Good morning to all. Today we are discussing about hysteresis. We shall now consider the hysteresis loop of the core as shown in figure. The waveform of the exciting current phi is obtained from the sinusoidal flux waveform and the multi-valued phi I characteristics of the core. The exciting current is non-sinusoidal as well as non-symmetrical with respect to the voltage waveform. The exciting current can be split into two components. One IC in phase with voltage accounting for the core losses and the other IM in phase with phi symmetrical with respect to E accounting for the magnetization of the core. The magnetizing component IM is the same exciting current in the hysteresis loop is neglected. The phasor diagram shown in figure, the exciting coil can therefore be represented by a resistance RC to represent the core loss and magnetizing inductance LM to represent the magnetizing of the core. In phasor diagram, only the fundamental component of the magnetizing current is considered. Exciting current with a hysteresis loop. The first one, loop and phi and I loop exciting current. The sinusoidal waveform in the exciting current, the maximum value of flux, the amplitude is known as the maximum magnitude of the quantity is known as amplitude. The varying the flux as well as the current. The next one is the phasor diagram. In this phasor diagram, the phi and I, that is magnetizing and demagnetizing and corrosive force, that is called hysteresis loop in the formation of phi and I. The next one is the equivalent circuit. In this equivalent circuit, then E is the voltage, reference voltage, IM is the magnetizing current, then change in flux, that means phi current value, the resultant current value. In the magnetic circuit, the resistance and reactance combination of the inductance in the equivalent circuit. Next, permanent magnet. A permanent magnet is capable of maintaining magnetic field without any excitation MMF provided to it. Permanent magnets are normally alloys of iron, nickel and cobalt. There are characterized by a large BH loop, high retentivity, high value of Br and high corrosive force, high value Hc. The alloys are subjected to the heat treatment resulting in mechanical hardness of the material. Permanent magnets are often referred to as hard iron and the magnetic material as a soft iron. Magnetization of permanent magnets. Consider the magnetic circuit shown in figure. Assume that the magnetic material is initially unmagnetized. A large MMF is applied and its removal, the flux density will remain at the residual value Br on the magnetization curve. If reversed magnetic field intensity of the magnitude H1 is now applied to the hard iron, the operating point moves to point B. If H1 is removed and reapplied, the BH follows a minor loop as shown in figure. The minor loop is narrow and for all practical purpose can be represented by the straight line BC known as recoil line. This line almost parallel to the tangent to the demagnetizing curve point A. The slope of the recoil is called the recoil permeability μr. For a Alnico magnet, it is a range of 3 to 5 μ0, whereas for ferritic magnets, it may be as low 1.2 μ0. As long as reversed magnetic field intensity does not exceed H1, the magnet may consider reassembly permanent. If a negative magnetic field intensity greater than H1 is applied, such as H2 is the flux density of permanent magnet will decreases to the value of B2. If H2 is removed, the operation will move along a new recoil line. The first one is a soft ion keeper, then hard ion. Then the ion core is a N is the number of turns. Permanent magnet system and its BH occurs. That means x-axis means magnetic field intensity, y-axis means flux density. In this point of view, the magnetizing value will be rises in the magnetization. Next, approximate design of permanent magnets. Let the permanent magnet be magnetized to the residual flux density denoted by point in figure 1.20. If the small soft ion keeper is removed, in the air gap will become the active region for most application as shown in figure. Then soft ion and hard ion. In the LM is the core, LG is the air gap, and permanent magnet with the keeper removed BH curve. In order to determine the resultant flux density, the magnet and the air gap, let us make the following assumption. There is no leakage or firing flux. No MMF is required for the soft ion. For Ampere circuit law, HM LM plus HG LG is equal to 0. HG is equal to minus LM into HM divided by LG. For continuity of flux, phi is equal to BM into AM, that is equal to PG into AG. Then PG is equal to mu naught into HG. Then BM is equal to maximum flux density is equal to mu naught into AG into LM divided by AM into LG into HM. Equation represents the straight line throughout the origin called shear line. The intersection of the shear line with the demagnetization curve B determines the operating values of B and H. Hard ion soft material with the keeper removed. If the keeper is now reinstated, the operating point moves up the coil line BC. This analysis indicates the operating point of permanent magnet with an air gap determined by the demagnetizing portion of BH loop and the dimension of the magnet and air gap. Then Vm is equal to Am into L. Then that is equal to Pg into Ag divided by Bm into Hg Lg divided by Hm. That is equal to Vm is equal to Pg whole squared into Vg divided by mu naught into Bm into Hm, where Vg gets the volume of the air gap. Thus, to establish flux density Vg in the air gap, volume of Vg, minimum volume of the hard ion is required. If the final operating point is located such that Bm into Hm product is a maximum, this quantity BmHm is known as the energy product of the hard ion. Next one is the permanent magnet materials. A family of alloys called alnico, aluminum, nickel, cobalt has been used for permanent magnet since 1930. Alnico has a high residual flux density. Ferrite permanent magnet materials have been used in the since 1950. These have lower residual flux density but very high corrosive force. So the demagnetization curve for ferrite D, which is ferrite. Since 1960, new classes permanent magnet is a rare earth permanent magnet has been developed. The rare earth permanent magnet material is combined the relatively high residual flux density and alnico type materials with greater conductivity than ferrites. These materials are compounds, iron, nickel and cobalt with one more of the rare earth elements. A commonly used combinations in cobalt, the demagnetization curve for the material. Another rare magnet material that has come into use recently, neodymium ion bond. The demagnetization curve, this alloy, the residual flux density, conductivity are both greater than those samaritan cobalt. It is expected that neodymium ion bond will be extensive permanent magnet applications. First one is a demagnetization curve Alnico 5. Then next one is a demagnetization curve Ferranti demagnet. Then next one is a determination of curve Samarian cobalt magnet neodymium ion bond magnet. Different types of magnetic materials can be used to achieve performance and cost trade-off. Ferritic PM materials are used to lowest cost, however the result low power density due to lower energy density of the ferritic material. Ferritic material also have positive temperature coefficient Br. Samarian cobalt magnets are for the high energy density, higher temperature operation and stable performance over a wide range of operating temperature. Due to this low temperature coefficient, Br is a corrosion resistance. However, the SMCO CO is the most expensive and is primarily is used in aerospace defense applications when high temperature operation without performance degradation is very critical. The most widely used BM material, nickel ion, is ion bond is equal to NdFeB type, which is high energy density and most effective due to overall reduction copper steel needs for a given torque rating of the motor. The main drawback NdFeB magnet negative temperature coefficient of Br and the need for corrosion protection. Nickel coating is used for NdFeB magnets to prevent corrosion. The next one is a simple example problem. The permanent magnet figure made up of Alnico 5 who demagnetization curve given the flux density 0.8 Tesla to be established in the air gap. When the keeper is removed, the air gap has a dimension Ag is equal to 2.5 cm squared and Ig is equal to 0.4 cm. The operating point of the demagnetization curve corresponding to the point which is product of HM BM maximum, and the operating point is BM is equal to 0.95 Tesla, HM is equal to 42 kilograms per meter. Determine the dimension IM and AM of the permanent magnet. Solution: IM is equal to LG HM into HG is equal to LG into PG divided by HM into mu naught. 0.4 into 10 to the power minus 2 into 0.8 divided by 42 into 10 to the power 3 into 4 pi into 10 to the power minus 7 is equal to LM is equal to 0.0606 meter. It is equal to 6.06 centimeter. AM is equal to PG into AG divided by BM. 0.8 into 2.5 into 10 to the power minus 4 divided by 0.95. That is equal to 2.105 centimeter squared. Statically and dynamically induced EMF. Generally, induced EMF is two types. Dynamically induced EMF, another one is a statically induced EMF. Dynamically induced EMF, we can see from the figure that conductor a light within a uniform magnetic field whose flux density uniform magnetic field in the flux density is a Weber meter cube. In the figure, the movement of the conductor shown in by the arrow line. When the conductor cuts across the right angles to the flux, let L, length of the conductor lying with the field and its move distance dx in the time. dt. Then change in flux B I dx Weber time dt is equal to second. According to the Faraday's law, EMF induced in the conductor and is this induced EMF is known as a dynamically induced EMF. The rate of change in flux linkage is equal to BL dx by dt. BL dx by dt is equal to BLB volt, where dx by dt is equal to is a velocity. If the conductor A moves at angle theta with the direction of flux shown in figure, then the induced EMF is equal to BLB sin theta. That is equal to LB vector into B vector. That is as cross product vector is equal to V vector into B vector. And example generator works production of dynamically induced EMF in the conductor. Then statically induced EMF is equal to statically induced EMF is two types, which is mutually induced EMF, another one is a self-induced EMF. Then mutually induced EMF occurs between two coils A and B. Two coils which are placed close to each other. If a coil A is joined to battery, which is variable resistance coil, B is connected sensitive galvanometer. When the switch is closed, current will flow through the coil A and produce a magnetic field which is partly linked with the B. As current through the A is changed, the flux linked with the B is also changed. According to Faraday's law, induced EMF produces in the coil B. This EMF is known as a mutually induced EMF. In the above example, there is no movement of any conductor. The flux variation being brought about the variation in the current strength only. Such an EMF induced in one coil by influence of the other coils called mutually induced EMF. Next, self-induced EMF. Self-induced EMF which is produced in the coil due to change of its own flux linked with it. If the current of the coil is changed, then the flux linked with the own turns will also change, which will produce an EMF that is called self-induced EMF. Thank you.